Let's learn about linked lists, which enable flexible but slower access. Imagine you're building a music playlist app. A user wants to insert a new song between track 3 and track 4. If you're using an array, here's what happens. You first find position 4. Then you shift every song from position 4 onward, one spot to the bottom, to make room for the new entry. This shifting process is expensive in terms of computational effort, especially if your playlist has hundreds or thousands of tracks, as each song beyond the insertion point needs to be physically moved. But what if you could just rewire a couple of connections and instantly splice the new song in without touching any other track? That's the core advantage of linked lists. Linked lists trade away the ability to jump directly to any position, something arrays do instantly, for the ability to insert and delete elements efficiently by simply updating pointers. Today, you'll see exactly how this trade-off works, why it matters, and when to choose linked lists over arrays. We'll start by exploring their access performance. This direct indexing is known as random access. Arrays excel at it, providing constant time, or O of 1, performance regardless of how large the array is, because the memory address of any element can be calculated immediately. Linked lists, however, require you to traverse from the beginning, checking each node sequentially. This sequential access means the time taken to reach a specific element grows linearly with the playlist size, represented as O of n. This illustrates the core trade-off. Arrays offer fast random access, while linked lists require sequential traversal. Understanding this structural difference is key to choosing the right data structure for your application. To fully grasp the power and mechanics of linked lists, we need to understand their fundamental building block, the node. Each node holds two crucial pieces of information: its actual data, like a song title, and a pointer, an address that tells it where to find the next node in the sequence. This simple structure, comprising data and a next pointer, is the essence of how linked lists operate. By linking these individual nodes together, one after another, we form a chain, or a linked list. The final node in the chain points to a null value, which signifies the end of the list. Traversing a linked list means starting from the first node and following each next pointer sequentially until you reach your desired position or the end of the list. This step-by-step movement is fundamental to how linked lists operate. This sequence of connected nodes, each holding a song, is exactly how a music playlist can be implemented using a linked list. The play button acts as our starting point, or head, of the list, from which we can begin playback. This table summarizes the core performance characteristics. Arrays offer constant time, random access, but insertions and deletions in the middle require shifting many elements, leading to linear time cost. Linked lists, however, excel at insertions and deletions because they only require updating a few pointers, making these operations constant time. Once the position is found, it's crucial to remember that while rewiring pointers is fast, finding the specific point to insert or delete in a linked list still requires a linear time traversal from the beginning, as we cannot jump directly to an arbitrary position. So, for scenarios with frequent insertions and deletions, the linked list emerges as the clear winner. By understanding the structural reasoning, you can now recognize these fundamental data structures in real systems, from browser caches and undue stacks to operating system schedulers. Let's build a linked list from scratch and see exactly how traversal works. Every linked list starts with a head, a pointer to the first node, which acts as the entry point to the entire data structure. Each node is identical in its fundamental structure. It holds some data and a pointer to the next node in the sequence. This modular design is key to how linked lists operate. As nodes are added, each one points to its successor. When the last node in the chain is reached, its next pointer is explicitly set to null, unequivocally signaling the end of the list and preventing further traversal. To traverse the list, you must begin at the head and methodically follow each next pointer one by one. There are no direct shortcuts to arbitrary positions within a linked list. This means that if you need to access the fifth element, for example, you are required to sequentially visit nodes 1, 2, 3, and 4 first. Each step builds upon the previous one. This sequential access model is fundamentally different from an array, where any element can be accessed directly using its index. This distinction highlights a core difference in their performance characteristics. The immediate trade-off is clear. Arrays provide O of 1's constant time instant access to any element, while linked lists require O of n linear time for access proportional to their length. This flexibility comes with an access cost. The strength and limitation of a linked list node lies in its singular focus. Each node only holds its own data and a reference to just one other node, its successor. This design means that to find any specific item, you must begin at the start and meticulously follow each next pointer step by step. The nullum pointer is more than just an empty slot. It's a critical signal. It unambiguously marks the end of the list, preventing any further traversal. This explicit termination condition is fundamental for correct list processing, ensuring algorithms know exactly when to stop. Now let's quantify the cost of traversal and see exactly why linked lists are slower for random access. Imagine you have a playlist with 50 tracks, and a user asks to play track number 50. In a linked list, you must start at the head and step through nodes 1, 2, 3, all the way to 50. That's 50 operations. This process directly reflects the time complexity of accessing an element in a linked list, which is big O of n. In contrast, an array provides direct indexing, allowing immediate access to any element based on its position, without sequential traversal. In an array, you jump directly to index 49 in a single step. The difference is dramatic, highlighting the constant time efficiency of array lookups, which is big O of 1. Let's visualize this fundamental difference. For linked lists, accessing position k requires big O of k time, which in the worst case is big O of n, where n is the length of the list. For arrays, it's always big O of 1, no matter how large the array is. This visual comparison demonstrates the scalability issue. As the list size increases, the performance gap between a linked list and an array for random access operations widens dramatically, emphasizing why big O of n is less efficient than big O of 1. For this task, this is the fundamental trade-off. Arrays excel at lookups and direct access, while random access is simply not a linked list strength. Understanding this distinction is crucial for choosing the right data structure, as big O of 1 is vastly superior to big O of n for access time. While arrays offer fast random access, linked lists often provide faster insertion and deletion operations, especially when modifying elements in the middle of a sequence. This highlights a different kind of strength for linked lists. Each data structure has its specific advantages and disadvantages. The key is to choose the right tool for the job, based on the operations you'll perform most frequently, aligning your choice with the strengths of the data structure. Now let's see why linked lists excel at insertion and deletion. The key is pointer rewiring. To insert a new node between two existing nodes, you only need to change two pointers: the previous node's next pointer and the new node's next pointer. Notice that no existing data moves or shifts. The operation relies purely on updating references, preparing for the new node's integration. The first assignment, track3.next equals new song, redirects track 3's next pointer from track 4 to the new song node, establishing the initial link. The second assignment, new song.next equals track 4, sets the new song's next pointer to track 4, completing the chain and seamlessly integrating the new node. This demonstrates O1 insertion for linked lists, as it requires only a fixed number of pointer updates regardless of the list's size. In contrast, inserting into an array requires shifting every element after the insertion point one position to the right. If you're inserting near the beginning of a large array, that's a lot of work. As you can see, to make space for new song, existing elements like track 4 and track 5 must be physically shifted to new memory locations. This physical movement of elements makes array insertion an ON operation, where n is the number of elements that need to be shifted. The contrast is immediately readable. The linked list required 2 pointer updates, while the array required 2 element shifts. The same logic applies to deletion. In a linked list, you just redirect 1 pointer to skip over the deleted node. Here, we simply update track 3's next pointer to bypass new song and point directly to track 4, effectively removing new song from the list's sequence. The physical removal of the node is a separate, non-critical step that doesn't impact the list's logical integrity or performance. Linked list deletion, like insertion, is an efficient O1 operation, requiring only a single pointer update. This scene has clearly demonstrated how linked lists achieve constant time insertion and deletion through pointer manipulation, a significant advantage over arrays which require costly element shifts. This decision tree visually synthesizes our understanding of data structure choices. It helps us quickly identify scenarios where the dynamic nature of a linked list with its efficient insertions and deletions offers a clear advantage over a fixed-size array, especially when fast random access isn't the primary need. Let's synthesize what we've learned and see where linked lists shine in real-world systems. Linked lists excel when you need frequent insertions and deletions, especially in the middle of a structure, and when you don't need fast random access. They're essential for dynamic structures that grow and shrink unpredictably. For example, an LRU cache uses a doubly linked list to efficiently promote recently accessed items both in O of one constant time, and to efficiently evict the least recently used item. This mechanism powers browser caches, databases, and even CPU memory management, ensuring optimal performance by keeping frequently used data readily available. Text editors use linked lists for undo stacks, allowing you to insert new undo states without shifting existing history. This is crucial for applications like text editors or design software where users frequently modify their work and need to revert changes quickly and efficiently. And sparse polynomials are represented as linked lists of terms, saving memory and allowing efficient term insertion. This approach is highly efficient for managing data where many elements are zero or absent, optimizing storage and computation by only storing non-zero terms. Operating systems use linked lists for job scheduling queues, where processes are added dynamically. This enqueue operation allows new tasks to join the queue efficiently and be removed dynamically. This dequeue operation enables dynamic process management, ensuring efficient resource allocation and task execution in complex systems by processing jobs in order. The choice between arrays and linked lists is strategic. Arrays are your tool when you need speed of access, offering constant time for random lookups. Linked lists are your tool when you need flexibility of structure, providing constant time for insertions and deletions once the position is known. Understanding this trade-off is fundamental for making informed design decisions. Master both arrays and linked lists, and you'll have the foundation to build efficient, real-world systems with confidence. This understanding helps you gain the skills employers demand. Ready to go deeper?